A catalytic converter is an emissions control device that converts toxic gases and pollutants in exhaust gas to less toxic pollutants by catalyzing a redox reaction. Catalytic converters are used with internal combustion engines fueled by either petrol or diesel, including lean burn engines as well as kerosene, heaters and stoves. The first widespread introduction of catalytic converters was in the United States automobile market. To comply with the U.S. Environmental Protection Agency stricter regulation of exhaust emissions, most gasoline-powered vehicles starting with the 1975 model year must be equipped with catalytic converters. These two-way converters combined oxygen with carbon monoxide and unburnt hydrocarbons to produce carbon dioxide and water. In 1981, two-way catalytic converters were rendered obsolete by three-way converters that also reduce oxides of nitrogen. However, two-way converters are still used for lean burn engines. Although catalytic converters are most commonly applied to exhaust systems in automobiles, they are also used on electrical generators, forklifts, mining equipment, trucks, buses, locomotives and motorcycles. They are also used on some wood stoves to control emissions. This is usually in response to government regulation, either through direct environmental regulation or through health and safety regulations. History. The catalytic converter was invented by Eugène Houdry, a French mechanical engineer and expert in catalytic oil refining, who moved to the United States in 1930. When the results of early studies of smog in Los Angeles were published, Houdry became concerned about the role of smokestack exhaust and automobile exhaust in air pollution and founded a company called Catalyst. Houdry first developed catalytic converters for smokestacks called CATs for short, and later developed catalytic converters for warehouse forklifts that used low-grade, unleaded gasoline. In the mid-1950s, he began research to develop catalytic converters for gasoline engines used on cars. He was awarded United States Patent 2,742,437 for his work. Widespread adoption of catalytic converters did not occur until more stringent emission control regulations forced the removal of the anti-knock agent tetraethyl lead from most types of gasoline. Lead is a catalyst poison, and would effectively disable a catalytic converter by forming a coating on the catalyst's surface. Catalytic converters were further developed by a series of engineers including John J. Mooney and Carl D. Keith at the Engelhard Corporation, creating the first production catalytic converter in 1973. William C. Thefel developed a catalytic combustor for gas turbines in the early 1970s, allowing combustion without significant formation of nitrogen oxides and carbon monoxide. Construction. The catalytic converter's construction is as follows. The catalysts support a substrate. For automotive catalytic converters, the core is usually a ceramic monolith with a honeycomb structure. Metallic foil monoliths made of canthal are used in applications where particularly high heat resistance is required. Either material is designed to provide a large surface area. The cordierite ceramic substrate used in most catalytic converters was invented by Rodney Bagley, Erwin Lachman and Ronald Lewis at Corning Glass, for which they were inducted into the National Inventors Hall of Fame in 2002. The washcoat. A washcoat is a carrier for the catalytic materials and is used to disperse the materials over a large surface area. Aluminum oxide, titanium dioxide, silicon dioxide, or a mixture of silica and alumina can be used. The catalytic materials are suspended in the washcoat prior to applying to the core. Washcoat materials are selected to form a rough, irregular surface, which greatly increases the surface area compared to the smooth surface of the bare substrate. This in turn maximizes the catalytically active surface available to react with the engine exhaust. The coat must retain its surface area and prevent sintering of the catalytic metal particles even at high temperatures. Ceria zirconia. These oxides are mainly added as oxygen storage promoters. The catalyst itself is most often a mix of precious metals. Platinum is the most active catalyst and is widely used, but is not suitable for all applications because of unwanted additional reactions and high cost. Palladium and rhodium are two other precious metals used. Rhodium is used as a reduction catalyst, palladium is used as an oxidation catalyst, and platinum is used both for reduction and oxidation. Cerium, iron, manganese and nickel are also used, although each has limitations. Nickel is not legal for use in the European Union because of its reaction with carbon monoxide into toxic nickel tetracarbonyl. Copper can be used everywhere except Japan. Upon failure, a catalytic converter can be recycled into scrap. The precious metals inside the converter, including platinum, palladium and rhodium, are extracted. Placement of catalytic converters. Catalytic converters require a temperature of 800 degrees Fahrenheit to efficiently convert harmful exhaust gases into inert ones, such as carbon dioxide and water vapor. So, first catalytic converters were placed close to the engine to ensure fast heating. However, such placing caused several problems, such as vapor lock. As an alternative, catalytic converters were moved to a third of the way back from the engine, and were then placed underneath the vehicle. In 1990s, integrated catalytic converters were developed, which, as the name suggests, were integrated into exhaust manifold assemblies. The high efficiency, safety and space-saving capability quickly earned them a popularity. Today, almost every new vehicle sold in the United States is equipped with integrated catalytic converters. Types. Two-way. A two-way catalytic converter has two simultaneous tasks: oxidation of carbon monoxide to carbon dioxide, 2CO plus O2 to CO2, oxidation of hydrocarbons to carbon dioxide and water, CxH2x plus 2 plus O2x CO2 plus H2O. This type of catalytic converter is widely used on diesel engines to reduce hydrocarbon and carbon monoxide emissions. They were also used on gasoline engines in American and Canadian market automobiles until 1981. Because of their inability to control oxides of nitrogen, they were superseded by three-way converters. Three-way catalytic converters have the additional advantage of controlling the emission of nitric oxide and nitrogen dioxide, which are precursors to acid rain and smog. Since 1981, three-way catalytic converters have been used in vehicle emission control systems in the United States and Canada. Many other countries have also adopted stringent vehicle emission regulations that in effect require three-way converters on gasoline-powered vehicles. The reduction and oxidation catalysts are typically contained in a common housing. However, in some instances, they may be housed separately. A three-way catalytic converter has three simultaneous tasks: reduction of nitrogen oxides to nitrogen and oxygen, 2NOx-XO2 plus N2, oxidation of carbon monoxide to carbon dioxide, 2CO plus O2 to CO2, oxidation of unburnt hydrocarbons to carbon dioxide and water, CxH2x plus 2 plus O2x CO2 plus H2O. These three reactions occur most efficiently when the catalytic converter receives exhaust from an engine running slightly above the stoichiometric point. For gasoline combustion, this ratio is between 14.6 and 14.8 parts air to 1 part fuel by weight. The ratio for autogas, natural gas and ethanol fuels is slightly different for each, requiring modified fuel system settings when using those fuels. In general, engines fitted with three-way catalytic converters are equipped with a computerized closed-loop feedback fuel injection system using one or more oxygen sensors. Though early in the deployment of three-way converters, carburetors equipped with feedback mixture control were used. Three-way converters are effective when the engine is operated within a narrow band of air-fuel ratios near the stoichiometric point, such that the exhaust gas composition oscillates between rich and lean. Conversion efficiency falls very rapidly when the engine is operated outside of this band. Under lean engine operation, the exhaust contains excess oxygen, and the reduction of NOx is not favored. Under rich conditions, the excess fuel consumes all of the available oxygen prior to the catalyst, leaving only oxygen stored in the catalyst available for the oxidation function. Closed-loop engine control systems are necessary for effective operation of three-way catalytic converters because of the continuous balancing required for effective NOx reduction and HC oxidation. The control system must prevent the NOx reduction catalyst from becoming fully oxidized, yet replenish the oxygen storage material so that its function as an oxidation catalyst is maintained. Three-way catalytic converters can store oxygen from the exhaust gas stream, usually when the air-fuel ratio goes lean. When sufficient oxygen is not available from the exhaust stream, the stored oxygen is released and consumed oxide. A lack of sufficient oxygen occurs either when oxygen derived from NOx reduction is unavailable or when certain maneuvers such as hard acceleration enrich the mixture beyond the ability of the converter to supply oxygen. Unwanted reactions. Unwanted reactions can occur in the three-way catalyst, such as the formation of odoriferous hydrogen sulfide and ammonia. Formation of each can be limited by modifications to the wash code and precious metals used. It is difficult to eliminate these byproducts entirely. Sulfur-free or low-sulfur fuels eliminate or reduce hydrogen sulfide. For example, when control of hydrogen sulfide emissions is desired, nickel or manganese is added to the wash coat. Both substances act to block the absorption of sulfur by the wash coat. Hydrogen sulfide is formed when the wash coat has absorbed sulfur during a low-temperature part of the operating cycle, which is then released during the high-temperature part of the cycle, and the sulfur combines with HC. Diesel engines for compression ignition. The most commonly used catalytic converter is the diesel oxidation catalyst. Stocks contain palladium, platinum and aluminium oxide, all of which serve as catalysts to oxidize the hydrocarbons and carbon monoxide with oxygen to form carbon dioxide and water. CxH2x plus 2 plus O2x CO2 plus H2O. These converters often operate at 90% efficiency, virtually eliminating diesel odor and helping reduce visible particulates. These catalysts are not active for NOx reduction because any reductant present would react first with the high concentration of O2 in diesel exhaust gas. Reduction in NOx emissions from compression ignition engines has previously been addressed by the addition of exhaust gas to incoming air charge, known as exhaust gas recirculation. In 2010, most light-duty diesel manufacturers in the U.S. added catalytic systems to the vehicles to meet new federal emissions requirements. There are two techniques that have been developed for the catalytic reduction of NOx emissions under lean exhaust conditions: selective catalytic reduction and the lean NOx trap and NOx absorber. Instead of precious metal-containing NOx absorbers, most manufacturers select restricted base metal SCR systems that use a reagent such as ammonia to reduce the NOx into nitrogen. Ammonia is supplied to the catalyst system by the injection of urea into the exhaust, which then undergoes thermal decomposition and hydrolysis into ammonia. One trademark product of urea solution, also referred to as diesel exhaust fluid, is AdBlue. Diesel exhaust contains relatively high levels of particulate matter, consisting largely of elemental carbon. Catalytic converters cannot clean up elemental carbon, though they do remove up to 90% of the soluble organic fraction, so particulates are cleaned up by a soot trap or diesel particulate filter. Historically, a DPF consists of a cordierite of silicon carbide substrate with a geometry that forces the exhaust flow through the substrate walls, leaving behind trapped soot particles. Contemporary DPFs can be manufactured from a variety of rare metals that provide superior performance. As the amount of soot trapped on the DPF increases, so does the back pressure in the exhaust system. Periodic regenerations are required to initiate combustion of the trapped soot and thereby reducing the exhaust back pressure. The amount of soot loaded on the DPF prior to regeneration may also be limited to prevent extreme exotherms from damaging the trap during regeneration. In the U.S., all on-road light, medium and heavy-duty vehicles powered by diesel and built after January 1, 2007, must meet diesel particulate emission limits, meaning that they effectively have to be equipped with a two-way catalytic converter and a diesel particulate filter. Note that this applies only to the diesel engine used in the vehicle, as long as the engine was manufactured before January 1, 2007. The vehicle is not required to have the DPF system. This led to an inventory run-up by engine manufacturers in late 2006 so they could continue selling pre-DPF vehicles well into 2007. During the regeneration cycle, most systems require the engine to consume more fuel in a relatively short amount of time in order to generate the high temperatures necessary for the cycle to complete. This adversely affects the overall fuel economy of vehicles equipped with DPF systems, especially in vehicles that are driven mostly in city conditions where frequent acceleration requires a larger amount of fuel to be burned and, therefore, more soot to collect in the exhaust system. Lean burn spark ignition engines. For lean burn spark ignition engines, an oxidation catalyst is used in the same manner as in a diesel engine. Emissions from lean burn spark ignition engines are very similar to emissions from a diesel compression ignition engine. Installation. Many vehicles have a close-coupled catalytic converter located near the engine's exhaust manifold. The converter heats up quickly due to its exposure to the very hot exhaust gases, enabling it to reduce undesirable emissions during the engine warm-up period. This is achieved by burning off the excess hydrocarbons which result from the extra rich mixture required for a cold start. When catalytic converters were first introduced, most vehicles used carburetors that provided a relatively rich air-fuel ratio. Oxygen levels in the exhaust stream were therefore generally insufficient for the catalytic reaction to occur efficiently. Most designs at the time therefore included secondary air injection, which injected air into the exhaust stream. This increased the available oxygen, allowing the catalyst to function as intended. Some three-way catalytic converter systems have air injection systems with the air injected between the first and second stages of the converter. As in two-way converters, this injected air provides oxygen for the oxidation reactions. An upstream air injection point, ahead of the catalytic converter, is also sometimes present to provide additional oxygen only during the engine warm-up period. This causes unburned fuel to ignite in the exhaust tract, thereby preventing it reaching the catalytic converter at all. This technique reduces the engine run time needed for the catalytic converter to reach its light-off or operating temperature. Most newer vehicles have electronic fuel injection systems, and do not require air injection systems in their exhausts. Instead, they provide a precisely controlled air-fuel mixture that quickly and continually cycles between lean and rich combustion. Oxygen sensors are used to monitor the exhaust oxygen content before and after the catalytic converter, and this information is used by the electronic control unit to adjust the fuel injection so as to prevent the first catalyst from becoming oxygen-loaded, while simultaneously ensuring the second catalyst is sufficiently oxygen-saturated. Damage. Catalyst poisoning occurs when the catalytic converter is exposed to exhaust containing substances that coat the working surfaces, so that they cannot contact and react with the exhaust. The most notable contaminant is lead, so vehicles equipped with catalytic converters can run only on unleaded fuel. Other common catalyst poisons include sulfur, manganese and silicon, which can enter the exhaust stream if the engine has a leak that allows coolant into the combustion chamber. Phosphorus is another catalyst contaminant. Although phosphorus is no longer used in gasoline, it was until recently widely used in engine oil anti-wear additives such as zinc dithiophosphate. Beginning in 2004, a limit of phosphorus concentration in engine oils was adopted in the API ADEM and ILSACGF4 specifications, depending on the contaminant. Catalyst poisoning can sometimes be reversed by running the engine under a very heavy load for an extended period of time. The increased exhaust temperature can sometimes vaporize or sublimate the contaminant, removing it from the catalytic surface. However, removal of lead deposits in this manner is usually not possible because of lead's high boiling point. Any condition that causes abnormally high levels of unburned hydrocarbons, raw or partially burnt fuel, to reach the converter will tend to significantly elevate its temperature, bringing the risk of a meltdown of the substrate and resultant catalytic deactivation and severe exhaust restriction. Vehicles equipped with OBD2 diagnostic systems are designed to alert the driver to a misfire condition by means of flashing the check engine light on the dashboard. Regulations. Emissions regulations vary considerably from jurisdiction to jurisdiction. Most automobile spark ignition engines in North America have been fitted with catalytic converters since 1975, and the technology used in non-automotive applications is generally based on automotive technology. Regulations for diesel engines are similarly varied, with some jurisdictions focusing on NOx emissions and others focusing on particulate emissions. This regulatory diversity is challenging for manufacturers of engines, as it may not be economical to design an engine to meet two sets of regulations. Regulations of fuel quality vary across jurisdictions. In North America, Europe, Japan and Hong Kong, gasoline and diesel fuel are highly regulated, and compressed natural gas and LPG are being reviewed for regulation. In most of Asia and Africa, the regulations are often lax. In some places, sulfur content of the fuel can reach 20,000 parts per million. Any sulfur in the fuel can be oxidized to SO2 or even SO3 in the combustion chamber. If sulfur passes over a catalyst, it may be further oxidized in the catalyst, i.e. SO2 may be further oxidized to SO3. Sulfur oxides are precursors to sulfuric acid, a major component of acid rain. While it is possible to add substances such as vanadium to the catalyst wash code to combat sulfur oxide formation, such addition will reduce the effectiveness of the catalyst. The most effective solution is to further refine fuel at the refinery to produce ultra-low sulfur diesel. Regulations in Japan, Europe and North America tightly restrict the amount of sulfur permitted in motor fuels. However, the direct financial expense of producing such clean fuel may make it impractical for use in developing countries. As a result, cities in these countries with high levels of vehicular traffic suffer from acid rain, which damages stone and woodwork of buildings, poisons humans and other animals, and damages local ecosystems at a very high financial cost. Negative aspects. Catalytic converters restrict the free flow of exhaust, which negatively affects vehicle performance and fuel economy, especially in older cars. Because early cars' carburetors were incapable of precise fuel-air mixture control, the car's catalytic converters could overheat and ignite flammable materials under the car. A 2006 test on a 1999 Honda Civic showed that removing the stock catalytic converter netted a 3% increase in horsepower. A new metallic core converter only cost the car 1% horsepower, compared to no converter. To some performance enthusiasts, this modest increase in power for very little cost encourages the removal or gutting of the catalytic converter. In such cases, the converter may be replaced by a welded-in section of ordinary pipe or a flanged test pipe, ostensibly meant to check if the converter is clogged, by comparing how the engine runs with and without the converter. This facilitates temporary reinstallation of the converter in order to pass an emission test. In many jurisdictions, it is illegal to remove or disable a catalytic converter for any reason other than its direct and immediate replacement. In the United States, for example, it is a violation of Section 203 of the 1990 Clean Air Act for a vehicle repair shop to remove a converter from a vehicle, or cause a converter to be removed from a vehicle, except in order to replace it with another converter, and Section 203 makes it illegal for any person to sell or to install any part that would bypass, defeat or render inoperative any emission control system, device or design element. Vehicles without functioning catalytic converters generally fail emission inspections. The automotive aftermarket applies high-flow converters for vehicles with upgraded engines, or whose owners prefer an exhaust system with larger than stock capacity. Warm-up period. Vehicles fitted with catalytic converters emit most of the total pollution during the first 5 minutes of engine operation, for example, before the catalytic converter has warmed up sufficiently to be fully effective. In 1995, Alpina introduced an electrically heated catalyst, called ECAT. It was used in Alpina's B1257 ECAT based on the BMW 750i. Heating coils inside the catalytic converter assemblies are electrified just after the engine is started, bringing the catalyst up to operating temperature very quickly to qualify the vehicle for low-emission vehicle designation. BMW later introduced the same heated catalyst, developed jointly by Imitec, Alpina and BMW, in its 750i in 1999. Some vehicles contain a precat, a small catalytic converter upstream of the main catalytic converter which heats up faster on vehicle startup, reducing the emissions associated with cold starts. A precat is most commonly used by an auto manufacturer when trying to attain the ultra-low emissions vehicle rating, such as on the Toyota MR2 Roadster. Environmental impact. Catalytic converters have proven to be reliable and effective in reducing noxious tailpipe emissions. However, they also have some shortcomings in use, and also adverse environmental impacts in production. An engine equipped with a three-way catalyst must run at the stoichiometric point, which means more fuel is consumed than in a lean burn engine. This means approximately 10% more CO2 emissions from the vehicle. Catalytic converter production requires palladium or platinum. Part of the world's supply of these precious metals is produced near Norilsk, Russia, where the industry has caused Norilsk to be added to Time magazine's list of most polluted places. Theft. Because of the external location and the use of valuable precious metals including platinum, palladium, rhodium and gold, converters are a target for thieves. The problem is especially common among late-model trucks and SUVs. Because of the high ground clearance and easily removed bolt-on catalytic converters, welded-on converters are also at risk of theft as they can be easily cut off. The techniques by thieves to quickly remove a converter, such as the use of a portable reciprocating saw, can often damage other components of the car. Damaged components, such as wiring or a fuel line, can have dangerous consequences. Rises in metal costs in the U.S. during recent years have led to a large increase in converter theft. A catalytic converter can cost more than $1,000 to replace.